Okay, how are you, everybody? I would like to take this opportunity to welcome some physical students into our very interesting workshop or lecture 4, where we are going to discuss about the reality of some of the basic logic gates, so we call them sometimes fundamental logic gates. My name is Olenjolai. It's the first time to meet me. I'm very happy to have you. I would like to ask you to join me. If you have gone through about some other workshops or lectures about digital electronics, this is the next one. And I want to tell you that if this is the first one, then you have to make sure you go through about the previous, because today we are going to build up on the foundation that we have built up in workshop 0, workshop 1, workshop 2, workshop 3. This is the 5th one. So I would like to ask you to stay connected and join me together into this interesting. But let me appreciate about some engineering students that I have in this class. How are you, students? How are you? Are you fine? Are you ready for digital electronics? Oh, that is good. So, let us go straight forward into the concept. Just to remind you, we say that we have 3 basic or fundamental logic gates. 3 basic or fundamental logic gates. The first one, we call it what, student? I don't hear you. The first one is called what? Please make sure that you participate and you pronounce these terminologies in order to keep them in your mind. Say naughty gate. Say naughty gate. Okay. And the second one, we call it AND gate. Say AND gate. Say AND gate. And the first one, we call it OR gate. So these are the 3 fundamental or basic logic gates that we have in digital electronics. We have discussed in previous workshop about NOT gate. Today, let us pay attention on the second, which is called the AND gate. AND gate. Say AND gate. And then the fundamental question, what is AND gate? What is AND gate? What is AND gate? What the meanings of AND gate? So simply say that the AND gate, we say that is the type of, this is the one of the types of basic logic gates that performs what? That performs the multiplication. That perform the multiplication of the binary multiplications of the binary inputs. That's the meaning of the naughty gate. So naughty gate is what? AND gate. Say AND gate. Say AND gate. Again, say AND gate. Again. Eh? Andigate or endigate? Andigate, eh? Not endigate. Aha. What is endigate? Eh? This is the type of what? Basic logic gate. That performs what? That perform what? That perform what? Multiplications of what? Binary inputs. Remember that all the computers, all the smartphones, all the iPads, they don't understand any other number rather than 1 and 0. Even the scientific calculator that you've been using in your A-level education, it cannot understand 2, 3, 4, 5, 7, 8, 9, 10, 11, or maybe used to integrate maybe a variable x. So it does not understand neither alphabets nor numbers, whether it's whole numbers or decimal numbers or irrational numbers. So the scientific calculator and most of all the digital devices, they just understand two numbers, 1 and 0. So because they understand 1 and 0, we need to process those 1 and 0. Just like ourselves, we used to say that, okay, if you want to say that we want to find the multiple, just take a 4 and multiply by 7. So we used to do multiplication. 4 times 7 is equal to what? Eh? 20. 28. Very good. 28. So 4 times 70 is what? 28. So this one we call it decimal number. Say decimal number. Say decimal number. Yes, I think that, let me just see, give you the concept a little bit. So in digital electronics, there are 4 types of numbers. There are 4 types of numbers. The first one is called the decimal number. Decimal number. Say decimal number. Say decimal number. So decimal number, this is what we know as a human being, 0 to 9. The second type of number that we have in digital electronics, we call it octo number. Say octo number. So octo number is 0 to 7. Then the third one, we call them binary number. Say binary number. So binary number is just 0 and 1. Wonderful. So few but powerful. Then the fourth one, we call it hexadecimal. Hexadecimal number. Say hexadecimal number. So hexadecimal number is just 0 to 9, and then the other ones is from A to F. So the computer, we as a human beings operating, we understand numbers, decimal numbers, very well. And also we understand alphabets. A, B, C, D, E. And they understand also symbols, plus or addition, subtraction, multiplication, division, square root. We understand those symbols as a human being. But the computer cannot understand them. Computer just needs 1 and 0. Your smartphones just need 1 and 0. So for that case, we say that this AND gate is the one of the part which is performing what? Multiplication. We as a human being, we can multiply this number, let's say 9 times 8 as a human being. We can multiply 9 times 8. For the latecomers, you're just welcome. This is the just beginning of the workshop. So it's the beginnings of workshop 5. Workshop 1, workshop 5. So 9 times 8 class is equal to what? 72. So the computer or any digital machine, even your scientific calculator, cannot understand 9, cannot understand 8. So 9 is actually presented by 80 bits. And also 8 is actually presented by, by 80 bits. So what the means of 80 bits? For instance, 9, you can find that it's 1, 0, 0, 0. Then we have 0, 0, 0, 0. So this is 9. Okay? This is 9 in terms of binary number. How many bits are this? 8. Right? 8, it's this one. 0, if I'm not mistaken. 0, 0, then 0. Then 0, 1, 1, 1. If I'm not mistaken. So if you want to, for you as a human being, 9 times 8 is very simple, right? But for the machine, it has to take these binary bits, 8 bits, and multiply with the other 8 bits to get another binary number, which represents what, 70. Do you see how digital is interesting? So you as a human being, it's difficult to remember that 9 is 0, 0, 0, 0. Can you? 9, number 9, it's 0, 0. You have 4, 0, 1, 0, 0, 0. So you don't know anything about decimal. It means you want to work at the computer. So if letter A, also letter 8 has 8 bits. And then this is uppercase. Lowercase has also 8 bits. You have to know it. How do you think life will be difficult? For instance, now you have, maybe you have almost contacts of 1,000 people. So each contact is actual. For instance, one contact you have saved Moses. So Moses, how many letters? 5, right? So but actual, behind the scene, behind your mobile phone, or behind the computer, or behind any digital device that have written Moses and see it on the display, actually these are the 5 times 80 bits. You have 0 and 1, which are 32. So whenever you press any keypad or any buttons or any keypad, it means actual, you are pressing letter K, but behind it, you are pressing 8 switches. Wow. You don't want to understand how your machines work. You just need them to tell, write him Moses, that's all. How is it write him? None of your business. But you're an engineer right now. You have to understand. Hey. Okay, so I think I made a mistake. The binary number for the 9, I forgot one here. Okay, you should not worry about whether I'm right or I'm not right. Just I want to build a concept in your mind. So simply, this is a very important gate because it can perform what? Multiplications of binary what? Input. So it can perform what the tables used to perform during our primary education. We were claiming table from 1 times 1. Do you remember? Ask your neighbor. Do you remember? 1 times 1, 1 times 2, 1 times 3. Ask your neighbor. Because your neighbor has forgotten about that. The whole night we are cramming because the next morning the teacher of mathematics will be in the class with a stick and the number of sticks. 5 times 5, quickly. But nowadays you say, you are retired, you have calculators, isn't it? For instance, 12 times 12. 44. 144. 12 times 13. That is another story. Do you see the human brain? It can memorize 5 times 5, you know. But 5 times 115, that's another story. You need a piece of paper and to work something. That is a human brain. So what we understand, we easily understand as a human beings, actually the computer does not understand. And what does a computer understand easily? We are the human being. That's why we have something called computer programming language. So computer programming language, we are writing something, we understand the human beings, but itself, it will interpret it into the machine language for the computer to understand. Right? So if you write K, you don't need to see the binary number of K. You just need to see K on the display, that's done. If you see the binary number, you send to the technician. I don't understand. My display, I think it has problems. I write K, then appear 01, 001. Are we together? Class, are we together? So this is the one of the important part that performing OT, multiplications of the binary number. You know about binary numbers, 0 and 1, but how you can multiply them. So this is the very important unit. Okay? Are we together? Are we together? So then we say that the AND gate may have 2 or 3 inputs with only one output. It's only one output. So remember that the minimum number of it means that the minimum number of inputs in the AND gates is 2. But you can have a 2-input AND gate, 3-input AND gate. But remember that the minimum number for the output is 1. So we have only one output in case of 40, in case of AND gate. For the NOT gate, the input is always 1 and the output is always 1. Bear that in your mind. Okay? Okay? You might be asking one day that, okay, draw the schematic circuit diagram of the NOT gate with 2 input and 3 output, and then we'll draw. Actually, it will be the first, it will be your own innovation because it doesn't exist. The simple response for that question, say, okay, the NOT gate with 2 inputs and 3 outputs does not exist. That's the response. Okay. Then the next is the second thing that we have to learn, or we have to grasp in our mind, a symbol of AND gate. The schematic symbol, this we call the schematic symbol. Schematic symbol of AND gate. Say schematic symbol of AND gate. Say schematic symbol of AND gate. So if you have AND gate with 2 inputs, this is the schematic symbol. Most of you know it. This is the schematic symbol. So this is inputs. So we call it input A, input B, and this is the output for the 2 input. If you have AND gate with 3 inputs, then we are going to have input 1, input 2, input 3. So this is inputs. And this is the output. So for the 3 input AND gate, we are going to have A, B, C. And this is the output. In most cases, this output we call it Q or Y, but just you can call it letter Y to present the output. So this is figure 1 for this workshop. The schematic symbol of 2 inputs and 3 inputs and the gate. So these are the concepts that we are familiar. Then another concept which is very important for the practical. Remember that, as I taught you, in most of the simulation software, these are the symbols that we expected to encounter. But physically, we don't have any components which exist with 2 inputs and 1 output. This also it's integrated circuit. Okay? Are we together? Okay. Then the next important part about NOT gate is the truth table. Truth table of 2 input NOT gate. Then at this point we'll have truth table of 3 inputs AND gate. I made a mistake here. This is AND gate. Stop writing and stop drawing. Let us draw together. So the NA truth table, it has mainly two parts. The first part we usually call inputs, and the second part we usually call output or outputs. So this is inputs and this is output. So in the inputs, because you have two inputs, we are going to have input A and input B. And output, let us call it Y. I said stop drawing, stop writing, listen and watch. Hello, 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 backbencher. So remember that we are writing the binary inputs by representing physical or actual the voltages. And also remember that when you're writing those binary inputs, we means that those are the possible combinations we might get in that particular logic gates. So when we are filling these cells of the truth table, you have to listen and you have to think. You should not, I know you have been writing just 0, 0 without any intention in your mind. Because remember that later on, we are going to verify this truth table practically. Okay? Okay? Okay. So what the concept that we use to deduce there? We say, suppose that A is the statement that I am teaching digital electronics. Digital electronics. Then this B is another statement that I'm teaching digital electronics. So another B is a statement that if I am not teaching digital electronics, then I'll go home. I know that this sentence is good for you. Okay? So what are the possible combinations? Listen. Listen, I say stop writing. The first possible combination, I am not teaching digital electronics and I'm not going home. So for that case, I'm not teaching, so this statement A is false and statement B is false. I am not teaching digital electronics. It's possible also at the same time, I am not going home. So I didn't make any choice. I rejected it or I'm not doing anything. So for that stage, you may say that if no any action that has been performed, we just see presented with the binary number or binary inputs of 0. So the first case, the binary input of A is 0 and binary inputs of B is 0. Are we together? Are we together? Then the second possibility is I am teaching digital electronics and also, but I am not going home. So for that case, this is statement A will be true, but statement B is false. Okay? The third possibility or the third possible combination, I am not teaching digital electronics, but I will go home. Right? I am not teaching what? Digital electronics, but I will go home. Then the last combination, I am teaching digital electronics, but also I am going home. So you should not claim. We usually let teach students that maybe just this one of input write 0, 0, 1, 1. And then this one just write 0, then alternate 0, 1, 0, 1. That is just a fundamental skills. But we are not writing these numbers because we need to write them, so because we are just we are entertaining you, but we are telling you the real situation. When we draw the schematic circuit diagrams of AND gate, we'll understand about that truth table. Okay? Okay, class? Okay? So 0 times 0. 0. 1 times 0. 0. Then 0 times 1. 0. 1 times 1. So remember that laydowns will have push button A and push button B. And then we expect it to have our outputs of different states to our light emitting diode. That is simple demonstrations or verification of the truth table of the AND gate. So what you have drawn should remain in your mind. Are we together? Then this is table now. So we call table 1 the truth table of AND gate of the two input AND gate. 2 input AND gate. For the AND gate with 3 inputs, let us just draw that. This is table. Remember that we have always the part we call it input and the part we call it output. So this is inputs, this is output. So then we have 3 inputs. First input, second input. So let us call this A. You may call, it's not compulsory to call A, you can call it P, Q, R. Then this one, let us call it Y. So remember that the principle of combination, this is the principle of possible combination. We say that the formula of possible combination of the truth table is 2 power n. So in NOT gate we had only 1 input, right? A 2 power 1. We had only 2 combinations. When the binary bit it is 0, it will be inverted into 1. And 1 is 1, it will be inverted into 0. That's all. Okay? For the AND gate with 2 inputs, we say that what the maximum number of the input? 2. 2 power 2, it is what? A 4. Then now we are discussing the AND gate with 3 input. So the value of n will be 3. Then 2 power 3, it is 2 times 2 times 2 is equal to what? 8. So we expect it to have 80 cells. The first one, the second one, the third one. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. How do we simplify the concept to the students? This is how we simplify. We just tell students, okay, in case you have 3 inputs, simple. Just write 0, 0, 0, 4 zeros, and 4, 1. For the next inputs, wonderful. Just write it 2, 0, 2 ones. 2, 0, 2 ones. Right? Then for the last 3 inputs, just write alternate 0, 1, 0, 1, 0, 1, 0, 1. Okay, so if this is the case, remember that the primary function of AND gate to multiply the bits, the binary inputs. Right? A. So simply, we are going to multiply. 0 times 0 times 0? 0. 0 times 0 times 1? 0. 0 times 1 times 0? 0 times 1 times 1? 0. Simple, eh? 1 times 0 times 0? 0. Okay, now you are saying 0. Later on, you'll say 1. 1 times 0 times 1? 0. 1 times 1 times 0? 0. 1 times 1 times 0? Hey, I know what you have prepared. Eh? 0 times 0 times 1 times 1 times 0? 0. 1 times 1 times 1 times 1 times 0 times 0 times 1. So that is what? 1. So it means that from these two truth tables, you can draw the conclusion that the output of the any AND gate, regardless of the number of the inputs, will be high if all the inputs are high. Okay? Okay? Stop writing. The output of the AND gate from this truth table, the outputs of the AND gate, remember that you have to write, this is table 2, the truth table of 40 of 3 input AND gate. So from this truth table, it means that the output of AND gate will be high or will be 1 if all the inputs are 1. So bear that in your mind. Whenever you are thinking about your designing, if you want to design a modern mechanical system, you have to remember that. Okay, I will use the AND gate, but you have to know the condition for the AND gate. It will be high if all the inputs are high. If one of the inputs is low, it goes low. So the output of the AND gate is high if all inputs are high. Remember, when you talk about high, it means binary bit number 1. Otherwise, the output is 0. Patie, kaeke mambo sawa. Don't ask him. Give her. So this is still simple, just a revision concept. Maybe you have forgotten for the number of years. Maybe you have learnt it 3 years or 4 years or 5 years ago. It's better to remind you and then let us keep the focus. Okay, so once we have these truth tables, then the next step that you have to pay attention right now, it's about the timing diagram. Timing diagram. Say timing diagram. Say timing diagrams of AND gate. Eh? Say timing diagrams of AND gate. Say timing diagrams of AND gate. Timing diagrams means these are the graphs of the logic gates. That's the meaning. So these graphs, we define them according to the time. And that time, we have 2 times in these graphs. One time is called the rise time. Say rise time. And the other one is called the falling time. Say falling time. Yes, so the digital signal will be rise up or will be rise. And also in some cases it will be falling. So you have rising time and falling time. That's why we call the graph timing what? Yeah. So let us draw the timing diagram for the 2 input AND gate. Stop drawing, please. Stop drawing. This is the one of the new. This is the new concept for the, I think for the number of students. So how many inputs do you have? 2. I say stop drawing. Stop drawing. Tell your neighbor stop drawing. First of all, greet your neighbor. Tell your neighbor hi. Are you fine? Did you discover that your neighbor is not fine? Okay. So let us come back to the class. Then we start with input A. This is our timing diagram. This is input A. Then we say that we need to have this. These are just the space of time. And this is the space of time. So 1, 2, 3. Then we have the other one, which is 4. Okay? So remember that for the input A, we have 0. And also, we have 1. 0, this one. 1, this one. Okay? Then we have 0, this one. And then we have 1. So simply, in terms of binary number, this is 0, this is 1. This is 0, this is 1. Is it clear? Is it clear? So when the path is actually raising from this point, this is the point where we have something called raising. Raising what? Raising time. Say raising time. And then when the bits is actually falling from the high state to the low state, this point we have a time we call it falling time. Say falling time. So this is raising, this is falling. This is raising, this is falling. Are we together? Let us draw the timing diagrams of input A. So the input A, the first bit is 0. Is it? A? The first bit is 0 for the input B. Right? The second bit is what? 0. So this is 0, this is 0. The third bit is what? 1. So this is bit 1. Then the next bit is what? Still 1, eh? So 1. So 1, 1. So for this case, we have only what? Raising what? Raising what? So the bit raised from 0 to 1. Or from low state to the high state. Are we together? Then now we are going to draw the timing diagram for the output. What do you have in output? So the output will represent out by letter Y. What the first bit in output? Let me, what the first bit in output? 0. So let me say the 0. 0. The second one? 0. Ask your neighbor, do you like 0? Ask your neighbor, do you like 0 in terms of marks? Your neighbor likes 0 in terms of digital, but not in terms of what? Marks. What the next bit? 0. Very good. What the next bit? 1. So this the next bit, it's what? It's 1. So 0, 0, 0, 1. So this is what? Figure what? Figure 3. The timing diagram of 2 input or 2 inputs and the gate. I think it is clear. Is it? If you have a question about what we have discussed, you may ask it. Hello? Okay, so one thing which I want just to clarify, the arrangements of this binary number might change. You should not claim that maybe all the zeros should be just in the first or in the second column or the second rows. No, these zeros might actually occupy either this cell or these cells or these cells or these cells. We may have 1, 1, 1. So you may start with 1, 1. And also the bits of the P might be the bits of the R, and the bits of R might be the bits of Q or bits of P. So one thing which I want to tell you that transform yourself from claiming to understanding. So the concept is actually you have to make sure that the appearance of all the three inputs should be bare. The arrangement is not important, as I said. The arrangement is not important. You may even swap that this one to be at this point and this 0, 0 to be at this point. You may swap that 0, 1, 1 to be at this point and then 1, 0, 0 to be at this point. So that's what you have to understand and have to bear in your mind. Is it clear? Is it clear? Okay. So I still need these two stable for the next part. I still need that two stable for the next part. So I don't want. Should I clean the timing diagram? Eh? Okay. So the next part now, we need to know the physical appearance. The physical and the schematic circuit. The physical appearance of this AND gate and so now the next concept is the schematic circuit diagram of AND gate. So example of this AND gate, we have it's what we used to start with SN, SN 74. So example, it's SN 74 HC 08N. So 04, it's not gate. 08, it's what? AND gate. Say AND gate. Yes, because you have been slumbering. So the schematic circuit diagram of 40 of HC 74, no, SN 74 HC 08 N AND gate. Okay, so the first thing that you have to know, the physical appearance of the AND gate. And this is the AND gate with only two inputs. Stop drawing, stop writing, listen and watch. This is a very important concept for you to understand. The SN 74HC08N, it has something called a notch. And also it's a integrated circuit with 7 pins. The first pin, the second pin, the third pin, the fourth pin, the fifth pin, the sixth pin, the seventh pin. On these sides also we have 7 pins. 1, 2, 3. But remember, for you have to use a ruler to draw them in a straight line. 4, 5, 6, 7. The notches actually give us the notifications and the common understanding worldwide where we have to start to number our pins. I say stop drawing, look and listen. So this is pin number 1. This is pin number 2. This is pin number 3. Pin number 4. Pin number 5. Pin number 6. Pin number 7. Pin number 8. Pin number 9. Pin number 10. Pin number 11. Pin number 12. Pin number 13. Pin number 14. Hello? That's one. Then the next one, remember that for the NOT gate we had X inverter. X inverter because they had 6 NOT gate. This one we call it quad. say quad, or quadrature AND gate, or quadrature integrated circuit. Moses? So for this IC, we have only 4 AND gates. This is the first one. So pin number 1 and pin number 2 are the input. And then pin number 3, it's output. It's output for the first AND gate. Okay? Okay? Then pin number 4, it's the input of the second AND gate. And pin number 6, it's output of the second AND gate. Leave me? Pin number 7, it's ground. Then on this side, we have also 2 AND gate. Pin number 9 and pin number 10, these are the input of the AND gate. And pin number 8, its output. Pin number 13 and pin number 12, these are the input of the first AND gate. And pin number 11, its output. The pin number 14, this we call VCC. This is the physical appearance of SN74HC08N. That's the physical appearance. That's how AND gate exists practically. So AND gate exists as integrated circuit. So you know nothing about integrated circuits, forget to understand or just forget how you can use or using the AND gates. Because the schematic is simple, you just need 2 inputs and 1 output. Are we together? So this will be our brain, our control unit. I said stop drawing, listen, watch. So how many AND gates do we have? So this one we call T4, or we call T quad, or we call T quad. Quadrature or quad AND gate. So the word quad means 4. Come from the word quadrature. Okay? Okay? So within the single integrated circuit, we have voting, 4 voting, and voting, and the gates. Okay, so let us draw now the schematic circuit diagram. Well, so we need to supply power to our integrated circuits, and the power is 5 volts. But that is positive power. Then we need to supply negative power, which we call T ground. So now we have provided power into our AND gate integrated circuit. Is it clear? Then the next step, we have to introduce the input. So to introduce the input, we need to use the pull-up. So VCC, or just we call it supply voltage, VS is 5 volt. Then we have what? So supply voltage is 5 volt. So we have resistor. Then we have the first push button. This is first push button. So you can call it push button number 1. But also we need another network where that you have supply voltage of 5 volt. This will be our second input. And also we have a pull-up resistor. And for this case, we have also the secondary push button. So this is the secondary push button. So this is push button number 2. Okay? I say stop writing, look on the blackboard. Some of you are still writing. Then the resistance of this pull-up resistor is 10 kilo ohm, and resistance of this pull-up resistor is 10 kilo ohm. So if that's the case, we always draw the input from this point where we have the connection of resistor and push button. And then, so this is the connection that we have, and connect it to the first pin of the OT of the AND gate. Then we take another, we draw another input here and connect to the second pin of the AND gate. So this one will represent the input A, and this one will represent the input B. Are we together? Are we together? Then we want to verify our output. So we need to have the load or the output unit. So the output unit will be just using, because we have a single, we have multiple inputs, but we have also single output. Then we connect to the ground. For this case, we have a LED, which is representing the load. And for this, and at this point, we have just the 100 ohm resistor. So then, this is our schematic circuit diagram. Moses. Take quickly. So I'm drawing the schematic circuit diagrams and then you're slumbering. Okay. So then, from these schematic circuit diagrams, we have our power source, VCC and ground. Okay? And also we have our input, input A, input B. And we have our controlling unit or our multiplier, which is the first AND gate. And also we have the output unit, which is actual, it will be changing the status of LED. We have used the 2 push button. We have used the 2 pull-up resistor in order to have 2 inputs. So in case of the 3, you'll need 3 pull-up resistor network. Okay. So with this schematic circuit diagram, before you draw it, first of all, is it clear at that point? No, it's not clear. Did you plan for the concept to be clear in your mind, or did you plan for the concept to be not clear in your mind? You plan to understand? Ask your neighbor, did you plan to understand, or you have planned not to understand? Because maybe the concept is not clear because you planned it. And you have been praying earnestly that today, God, help me not to understand digital electronics. Help me not to understand. Yes, there is that kind of prayer. For instance, you are praying right now, the class to end. Okay. So let us come back. I think that I've taught you 2 concepts at the same time. Stop writing, stop drawing. I'll give you just 1 minute to draw. This is the physical appearance of the AND gate, where that actually we used to draw its schematic symbol like this one. So physically, there is no any electronics components that will buy, which has just a single AND gate. AND gates are always manufactured by different manufacturing industries, whether it is transistor logic AND gate, or it is complementary metal oxide semiconductor AND gates, because we have 2, we have 2 architectures. There is TTL architecture and CMOS architecture. Hello? Hey! What are you doing? So I've been reminding you. Keep this mobile phone for me. You'll give me. This is mine, eh? Okay. So this is the schematic symbol of the AND gate, single AND gate. But AND gates exist in integrated circuit or IC, right? So because there's 2 inputs and 1 outputs, and remember that these ICs, they have 14 pins, 2 pins for power, 1 for ground, the other one's for what? For the positive power supply. Are we together? Then I drew the physical appearance of the different AND gates within a single SN74HC08. Remember, NOT gate is 04. AND gate 08. Are we together? Are we together? So internally, when you've been given that, oh, this is the AND gate, I see. Internally, if it is 2 input AND gate, internally it has 4 AND gates. It's just like a NOT gate. It had 6 UT. The NOT gate I see, it had 6 UT. NOT gates. Okay? Hello, what's going on to your neighbor? Okay, so your neighbor has woke up. Then, because you have 4 AND gates, it depends to your design and it depends to your demand. You may use all the 4 AND gates. You may use 1, you may use 2, you may use 3, you may use all the 4 AND gates. The advantage of having this integrated circuit, for instance, if you have the system where you have 8 sensors, you just need 1 AND gate IC. Because the first sensor will connect here, connect here, connect here, connect here. The second, the fifth one, connect here, and this one. The 7th one, and the 8th one. So you just need 1 integrated circuit, which is actually occupy very small space, and you have advantage of different AND gates. Are we together? Up to that point, are we together? So this is the physical appearance of 40 of the SN74HC08 and 2 input AND gate. Then afterward, we know now the internal structure of the AND gate. How can you use it practically? So the way that we can use it practically, simple. We just say that I have talked about pull-up resistor network. Pull-up, just leave it. Pull-up resistor network. Where in this pull-up resistor network, we just need to connect the resistor and the push button. Okay? So because we have 2 inputs, we need 2 resistor network. The first one is this one, the second one is this one. Class, listen. With the first pull-up resistor network, we need to supply power. We need the pull-up resistor, which say 10 kilo ohm, and we need the push button number 1. So this one will be supplying the inputs to the pin number 1 of SN74HC08N. Okay? Then we have another pull-up resistor network. This is 5 volt, and this is 10 kilo ohm, resist of the 10 kilo ohm, and also you have a push button number 2. And this is connected to the ground. So this one will be supplying the inputs to the pin number 2. And then we have to take the outputs to change the status, because we can see the light emitted by the light emitting diode. So we use this one as just for the matter or for the purpose of learning, for the learning purpose. But in reality or in industries, we don't have LED. We can just have another circuit or another system, which might be digital, or mostly digital or analog to digital converter, or digital to analog converter. And in case of the inputs, you might have a sequence or a number, a series of the sensors. Are we together? Remember that this pull-up resistor network and this LED it's just for the learning purpose, to understand how we can use AND gates practically. Are we together? So this is push button number 1, push button number 2, ground, ground, ground. Then this is pull-up resistor number 2, pull-up resistor number 1. So we have connected them to the inputs of the AND gate. In case that you want to use the second AND gate, simple. You just connect the input from the pull-up resistor network to pin number 4. And you have to connect the inputs, the second input, the pin number 5. And you draw the output from the pin number 6. That's all. Okay? In case you want to use the third AND gate, So you just connect the input of pull-up resistor network number 1 to pin number 9, and you connect the just the input from the pull-up resistor number 2 to the pin number 10. The same story for AND gate number 4, or the first AND gate. Now, is it clear? Is it clear? So now, what the principle of operation? If that concept is clear, I thank God if you've understood. Now, let us come to the last part, that how do we verify the truth table of two inputs AND gates by using this AND gate? How can we verify? So remember the principle, the concepts I taught you in previous classes. When the push button is not pressed, what the voltage across it? When the push button is not crossed, what the potential difference across it? 5, or supply voltage. So when this push button is not pressed, its resistance is infinity, and all the supply voltage will drop across it. Right? Right? When the push button is pressed, what will be the potential drop across it? 0 what? 0 mangoes or 0 chairs? 0 volt. The same story for the second pull-up resistor. So let us verify this truth table on this schematic circuit diagram. What the first binary input? 0. What the second binary input? 0. So you can verify it if the first push button is pressed and the second push button pressed simultaneously. Then we'll have the state 0, 0. 0 times 0, 0. LED will be off. That's why we have outputs of 0. May I repeat? You heard it, but you forgot it. First in, first out. Some students told me, we heard it, but once you finish, once the sentence ended, then it has disappeared. Let me repeat. This is our truth table. This is what we know from the advanced from electronic science. Okay? Okay? And this is what we have to learn from the engineering perspective. The first bit is what class? The first bit. So suppose that this is input A, this is input B. What the first bit here? Say it loudly. 0. How can we get 0? If how can we get 0 in input A? We have to press push button number 1. We'll have 0 voltage fed to the first pin of the AND gate AC. Are we together? So for that case, the input at this point, let me delete this 1 and 0 and 2 for the demonstration. So if this push button is pressed, the input bits is 0. Are we together? What the status of the first C of the OT of the second input, which is B? Status is what? 0. How can we get 0 in this pull-up resistor network number 2? We have to press this push button. Right? Once we press it, we have bit number what? 0. So 0 times 0. So the output is what? 0. That's why we have 0 here. So if you have 0 voltage, because 0 represents, remember that according to our philosophy, we say that 5 volt represents bit number 1. 0 volt represents bit number 0. So if you have 0 volt, then the LED will not turn on, because the LED needs some supply voltage for it to turn on or to give out light. Hello? So that is the first condition. Okay? We move the second condition. The second condition, the bits of the input A, it's 1. Hello? Sierra's company. The bit of input A, it is what? A? 1. How can we get 1? We don't press push button number 1. Okay? If you don't press push button number 1, the potential difference across this push button is 5 volt. Right? So 5 volt representing what? Bit number. Bit number. So if you have 5 volt, then the bits at this moment, it's 1. Okay? Then what the status of the input be? 0. How can we get 0 in this pull-up resistor network number 2? We have to press what? Push button. So here we have what? 0. Right? 1 times 0? 0. So the output is what? 0. The LED should be remain what? Off. That's why we have bit number 0. Hey, tell your neighbor, this is digital electronics. You see numbers, immediately you see electronics component. Then we go for the third possibility. And what the status of input A? A? How can we get 0 here? We press, So once we press, we get what? 0. Right? A? And what the status of input be? 1. How can you achieve? We don't press push button number 2. Then the input bits will be what? 1. Are we together? This is the multiplier. Multiplying the what? The binary inputs. 0 times 1. 0 times 1? 0. So the output is what? 0. The LED will be remaining what? Off. Say off. Say off. Then we are going to, let us move to the last combination. So the last combination is the status of input A is 1. How can we get 1? From push button number 1? We don't press it. Right? The status of input B is what? 1. How can we get it? We don't press the second push button. So here we have, my friend here is asking me why. So we don't press push button number 1. The potential drops is 5. Its bits is 1. Right? We don't press push button number 2. The potential drops across it's 1. It's 5 volts. The binary bits is 1. 1 times 1. 1. 1 times 1 is what? 1. The LED will turn on. Then we have already verified the truth table of 2 input and the gate. That's the end of the story. Questions? Remember that we don't write those information. So I'll be moving to another gate right now. You have write in your brain. You like writing. Sometimes you have to talk by diagrams. Engineering is all about numbers, formula, diagrams, tables, and what? Graphs. So keep what you've understood. Or you may write down. You may just take a note. You are allowed also to write down what you have said. The principle of operation is just simple. Okay, so the name of this first pin, stop writing. The name of this first pin, remember that this is just for the demonstration purpose. Right? The name of this first pin is 1A, and this one is 1B, and this one is 1Y. The name of this pin is 2A, and this one is 2B, and this one is 2Y. The name of this pin is what? 3Y, 3A, 3B. Then the names of this one is what? 4Y, 4A, 4B. That's all. So in simulation, we are going actually to draw this is schematic circuit diagram. But also another thing that which I want to tell you practically, we'll build these schematic circuit diagrams on breadboard, and we'll see or we'll verify that truth table. So I have taught you for the truth table, I have taught you how you can verify the 2 input and the gate. Your homework, you have to go and do the same and draw the schematic circuit diagram of 3 input and the gate. and then write the principle of operation. Once you manage to do so, you have already understood the AND gate, theoretically and practically. Do you have a question, madam? No. Do you have answers so I can ask you a question? So, may I clean here? Okay, so this is all about discussion about AND gate. Let us finish with OR gate. Say OR gate. So what is OR gate? OR gate, you say that this is the type of basic logic gate that performs the addition of binary inputs. It's simple. Once you understood the AND gate, just this is vice versa. Binary inputs. So the AND gate perform what? Multiplication. Say multiplication. In decimal numbers, when we're learning about numbers, we have been taught about basic operation. Say basic operation. Say basic. In mathematics, you have only 4 basic operations, right? The first one is what? Addition. The second one is what? Subtraction. Multiplication. Division. Do you remember about body mass? Ask your neighbor. Do you remember about body mass? What the long terms of body mass? In Swahili, we used to call it magaziyuto. Ask your neighbor. Do you remember about magaziyuto? So your neighbor seems like he or she has never heard about that, yeah? Because now your neighbor is a veteran. So this one perform addition. Remember that in digital electronics, we don't have subtraction, we don't have division. We just have addition and multiplication. That's all. So we perform subtraction by performing addition. And we perform division by performing multiplication. Digital is very interesting. So that's why you will never hear that this is the logic gate for subtraction. This is the logic gate for division. No. Division is just multiplication. And the subtraction is just addition. However, in your scientific calculator, you can subtract numbers. Yes, you can subtract number in terms of decimal. But behind, you are adding them. In your scientific calculator, you can divide numbers. For example, 20 over 5. 20 over 5? 4. So the digital circuits cannot understand 20 over 5. First of all, that operation is not there. So 20 over 5 is just like you have 20 oranges, then you want to divide. So you think a number that should be multiplied until you get 20. Are we together? Then we say that the OR gate may have either 2 inputs or 3 inputs. So the OR gate may have either 2 inputs or 3 inputs. Then the next concept that you have to understand as engineers, schematic symbol of OR gate. So the schematic symbol depends on the number of the input. So this is input, this is output. So input A, input B. output y. If the OR gate with 3 inputs, A, B, C, these are the inputs, this is the output. Figure what? The schematic symbols of OR gate. Then once we have covered about once we have covered about the schematic symbol, then we can just focus on the truth table. Truth table of OR gate. Battery to input OR gate. So this is input A, input B, input Y. Stop drawing, stop writing, look on the blackboard. So let us start with just the true possible combinations of input A and input B. I said stop writing. So we have 1 over 1, we say that we'll get 1, then we have a remainder of 1. Just like when you have 9 plus 9, we get 18. So write 8, we keep 1. Right? A? Class. For instance, 9 plus 9 is equal to what? 18. You write 8, you keep 1. In binary number, in case that we have 1 plus 1, we get what? 1. Then you have a remainder of 1. Okay? Okay? Have a remainder of 0. Sorry. Remainder of 0. But anyway, it means, no, we have a remainder of 1. 1 plus 1, we have a remainder of 1. Okay. Then we have 0, 1. Another state. So 0 plus 1 is 1. Remainder is 0. It's just like if you have 4 plus 4. You get 8. Remainder is 0. Right? Should not bother about how we do additions because it's a little bit challenging. Then we have 1. Then we have 0. So 1 plus 0, it's 1. Remainder, it's 0. Forget about that remainder. We need just the addition. That's all. Then you have 0, we have 0. 0 plus 0. So I have reversed this truth table from the one that you know. Moses. Moses is Mosesing. So this is table 3, the truth table. Moses is what? Of 2. Ediga Moses is what? Moses. 2 input OR gate. Lim is no longer liming right now, but Moses is Moses. Okay, so this is the same. So the homework, remember that I left you one homework to draw this one to verify the principle of operation for 3 inputs. And then right now, draw the truth table for the 3 inputs of the OR gate. So you'll be drawing, so the second task, right? Draw the truth table of 3 input OR gate. Right? Simple. Is it? Yeah. So now let me focus the next part, which is timing diagram. Timing diagram of what? Timing diagram of 2 input OR gate. So we have input A. So at input A, 1, So 1, 1, 1, 1, 1. Ask your neighbor, do you like 1? In exam, do you like 1 out of 20? Ask your neighbor, do you expect to get 1 of digital? 1 is good in digital because the maximum number. So 1 is like 100. So if you don't like 1, so in case that you have scored 20 out of 20, you say, okay, I scored 1 in digital language. And when you score 0, then the response is say that bit 0, bit 0, bit 0. Okay, so this is input A. What the state for the input A? Stop writing. A, agape, what the state of input A? High. Again, the second bit for the input A? 1. Who told you 1? Is this 1? Oh, you're extremely tired. This is 1. According to that is 1. Then the next A1. So this is 1. Then the next A. You don't pronounce. The next is what? 0. That's input A. Simple. Then for the input B, the first bit is what? A1. Agape call it high. And the next bit is what? 1 again. And the next bits are what? 0. Next one is what? 0. You've understood the concept. 0, 0. So now we are going to do the OR. Perform the OR. The addition. 1 plus 1. 1 plus 1. 1 plus 1 is 1. 1 plus 1 is what? In decimal. 1 plus 1 is 2. But in digital, 1 plus 1 is what? 1. We have a remainder of what? 1. Because the maximum number in digital is 1. Right? It's just like the maximum number in decimal is 9. And a number exceeding 9 will be writing and they have a reminder. Or you have to call to you are carrying in. So 1 plus 1, you say the 1, A1. Then 0 plus 1. 1. Then 1 plus 0. A1. Then 0 plus 0. 0. So do you see that these timing diagrams are different from one gate to another gate? But for you, you'll be cramming. Okay, I'll be just rising up, falling down, rising up, falling down. You don't care. So this is figure what? A? 6C. Are you still in figure 4? You need deliverance. The timing diagrams of 40 of 2 input OR gate. The next, the last concept is the schematic circuit diagram. Do you see how digital is simple? Tell your neighbor, digital is simple. Your neighbor doesn't want to appreciate that digital is simple, eh? But remember that here you have a homework and I left another homework there, right? Yes. So I have 3 questions for the homework today. I've already stated 2. There's the third one that's coming. Make sure that you do those homework questions because they're very important. Then schematic circuit diagrams of what? So the example of OR gate, example of OR gate, say example of OR gate. Say example of OR gate. SN74 HC32N. So SN74 04N, it's not a gate, right? SN74 HC08N, it's AND gate. And SN74 HC32N, it's what? It's what? All gate. Very good, Edgar. It's what? All gate. So so when you go to the electronic shop, then you can say, okay, excuse me, sir, can I buy the SN74HC32N integrated circuit? The answer is what? Yes. How much does this cost? 5,000. It's very cheap. What if I just give you 10,000 and you keep the change? Aha! You won't hear that language in Bongo land. There is no keep the change in Bongo. In Bongo, the simple business language is, what is this discount? Discount is important. Okay. So are you done? I want to move here. So are you done? Can you move together? Oh, you're still there. You're still there. Okay. Hello? Hello? Hello, DJ? Okay. So now let us discuss about the schematic circuit diagrams of SN74 HC32N OR gate. Also it is quad or quadrature OR gate. Its physical appearance is the same with this one of the AND gate. That's why that you just have to remember for the AND gate. But just the appearance will be a little bit different. This is for the OR gate. And for this case, we have also another OR gate like this. We have another OR gate. For this one, we have another OR gate. Oh, this is wrong, eh? This is bad. We are about to end our workshop or lecture 4. Then, for this case, the same configuration. just the schematic symbol of AND gate differ from the schematic symbol of what? OR gate. But we still have 4 OR gates within it. Okay? Then the input network is just like what you had in the AND gate. But the principle of operation is different. Ask your neighbor, do you see how digital is simple? Eh? First of all, ask your neighbor, do you like digital electronics? That's the first question. Then the next one, do you see that how digital it is simple? Agape knows the response of her neighbor. However, that Agape's neighbor is smiling, but smiling with sadness that this digital will kill me. So that the schematic are schematic circuit diagrams of OR gate. So another point that we have to make a change is this point. This is 32, however that you want to rush, but you have to remember some points that we have to do an adjustment. And this is figure what? Agape's friend? 10? 7. Okay, yes, thank you very much, 7. So the schematic circuit diagram of 40, SNHC, this is 32, and OR gate. Remember that if you want to design modern mechanical system without a knowledge of digital electronics, you will never have or you will never be able to design modern mechanical system. So don't draw it. Let me explain the principle of operation, and then you will draw it while you understand what you are drawing it. Remember that I will not write the principle of operation. There are 4 principles of operation there. I won't write. I will just explain. You keep in your mind. Then that's done because you have to learn by using diagrams, and that's the importance of diagrams. Okay? And be careful with these diagrams, right? Okay. Take considerations of them. This is push button number 1, push button number 2, right? We want to verify what it, the truth table of 2 inputs of all what it? OR gate. Say OR gate. And what the status of input A?
1.
A?
1.
A? 1. How can you have bit number 1 in push button number 1? Don't press. So the output voltage here will be what? 5 volt. Right? And then so you feed what here? 1. Then the first status for the input be 1. What should you do for the push button number 2? Don't press. Tell your neighbor, don't press. Don't press. And tell your neighbor, my neighbor, make sure that today you dream. Don't press. Or you dream about digital. Okay, so we don't press, then we are going to have bit number what? 1. Right? 1 plus 1 in OR gate. A. 1 remainder of 40 of 1. So if the output is 1, what will happen to the LED? It will turn on. Why? Because we have the supply voltage of 5 volt. Are we together? The second, what the status of input A? How can you achieve it from the pull-up resistor network number 1? We press it. We have 0 volt, right? And then we have 0 bit. Okay? For the input pin number A or input 1A, right? Then the status of input B is what? 1. How can you achieve it? Don't press. That is good. Press, don't press. Press, don't press. So today when you sleep, press, don't press. Don't press. The concept will be written in your subconscious mind, right? So don't press. So here we have 1. 0 plus 1. Or 0 or 1. 1, right? So the output is what? 1. What will happen to the LED? On. You just meet somebody, LED, you just tell your neighbor, on agape, on. Agape smiling, smiling, agape smiling. So LED will turn what? On. If it won't turn on, it means something happened. There is a problem there. Because these theories will take us into practical. So this song that we are singing will verify. I will give you the components and verify it for us. So just to sing it, Mungu ibariki Tanzania. Okay, the second one. What the status of input A? 1. Even Lim said 1. 1, eh? How can you achieve 1? Don't press what? Push button number 1. Right? So we'll have what? 1. Bit number 1 here. Then the status for the second, for the input B? 0. Right? How can I achieve 0? How can I achieve 0? How can I achieve 0? What? Press. Press which button? A? PB2. PB2 is abbreviation of what? Push button. Push button number 2, right? Yes, because I've said that PB2, PB1, PB2, PB1. That's the next level of cramming. Okay? So here we are going to have what? 0. 0 here, right? 1 or 0? 1. So what will happen to the LED? It turn on. If it won't turn on, something wrong. Figure out the problem as an engineer, as a digital mechanical engineer. Then lastly, what the status of input A? How can you achieve it? Press. Press what? Can you press your neighbor? First of all, press your neighbor. Show your neighbor how are you going to press that push button. So we press, we'll have 0. And then the second one, the fourth input, the fourth status of the input B, 0. How can you achieve? Don't press, right? So you have 0. 0 or 0? 0. What will happen to the LED? It turns what? Off. Then that's all. So you just need the electronics components now to verify, to use the basic logic gates practically. That's what you need to do right now, because you know the principle and you know how to connect them. Remember that when you go for the practical, you just need to connect the components according to this figure. So we won't have any other further discussion. For that case, we'll give you the components, then you build the circuit, you test. Okay? Is it clear? Class, is it clear? So remember, the input might be either a sensor, the input might be another digital circuit. So you should not claim that, just the push button. No. Push button, this the R, A, E, O, U of the input digital in digital electronics system. So if it is clear, I would like to say this is the end of workshop 4. And actually, I would like to, the third question for homework. So the third question for the homework, after drawing the truth table of 3 input OR gate, you have to draw the schematic circuit diagram of 3 input OR gate. So question number 1, you have to draw the schematic circuit diagram of what? Of 3 input AND gate. Right? The second question is what? Draw the truth table of 3 input OR gate. The third question is what? Draw the schematic circuit diagrams of what? 3 input OR gate. And also explain the principle of operation. Once you do those 3 questions, you are a very good student in basic logic gates. But if you wait until it means you will be asked by somebody, or you'll encounter in some points, then you find that digital electronics, it is tough. So thank you very much, and I would like to say that this is the end. Welcome in the next workshop. That's workshop 5, when we'll be discussing about universal logic gates. So we are done. I've given you the fundamental skills about the basic logic gates. In the next workshop, workshop 5, we'll be discussing about universal logic gates, which are NAND gate and the NOR gate. Just the 2 gates. But they have changed the world since the invention of them. That's why we have portable computers, we have portable scientific calculators. But previously, the calculator is very huge. You cannot carry it. You have to leave it at home. And it cannot just perform 4 basic operations: addition, subtraction, multiplication, and division. It cannot perform the square root. Okay, so thank you very much. See you in the next workshop. Be blessed.
Tanzania.